This afternoon I'll be talking about nutrient management after soil amelioration. So this work follows quite a large body of work around soil amelioration in WA. So this figure provides a bit of a chronosequence of the work that's been done and in progress. So I guess at an industry level, we've built quite a lot of capacity around diagnosing soil constraints, implementing the amelioration treatments, getting crops up and away. But the driver for this project was really around, is there more yield to be made up by doing something different with nutrition? And so there's a few components to that. The first is around identifying changes in soil nutrient availability, identifying changes in demand, and then finally optimising the efficiency of applied nutrients. So I'm going to focus on the last two components in the presentation today. So what I'll do is step through a few of our field experiments as case studies. And the first that I'll focus on is a 2-year study that we've set up in Tammin on a deep yellow sand, heavily compacted, where we're interested in how deep ripping changes nitrogen use efficiency. So it's a fairly simple design in one way, in that the design is just a factorial of tillage treatments by nitrogen rate, but we're implementing that over 2 years. Our interest there is how the dose response curve changes over the first and second year. And we've also got 15N urea plots in there where we want to quantify fertiliser use efficiency and also where that fertiliser N actually ends up. The figure on the right is soil strength profiles taken just after seeding. You can see in the black line there, peak soil strength is around 4.5 megapascals. That's an extremely hard soil. And the yellow line is where we've done the deep ripping treatment. So we've done a pretty effective job at reducing soil strength at that site. So this slide summarises the responses that we have so far. So we were testing for an interaction and we found it. So the interaction here is that deep ripping has changed the yield and economic response to applied N. So if you start with the figure on the left-hand side, the black line is the untreated control, the brown is the deep ripping, and the interaction here is that the difference between those two lines gets bigger as the nitrogen rate increases. So just to pick out some numbers for you, where we've applied 40 of N, the untreated control is 1.6 tonne, the deep ripping 2.7. Going out to at 120 of N, the untreated control is 2 tonne, the deep ripped is 3.8 tonne. So a highly significant interaction there, and the outcome in terms of yield is pretty obvious. When we look at economics, the differences fall out, I guess, more clearly. So based on the recent increase in fertiliser prices, I've priced 2 scenarios here. The first the middle figure is net return with urea at $511 a tonne, 5-year average leading into this year. And that's also costing deep ripping at $90 a hectare, so the upper end of what you would cost for that operation. And the figure on the right-hand side is with urea at $1,000 a tonne. So in both cases, the interaction was significant. And if you look at the untreated control, so the black line in the middle slide, what you'll see is that even though there is an increase in net return, really there isn't a significant difference between 40 out to 160 of N. So we've got a very flat economic response curve there, whereas with the deep ripping, it is profitable to apply N, and there is even a step up in profit from N at the highest rates. So even accounting for that $90 per hectare with deep ripping, it's profitable in the first year. When you look at the scenario at $1,000 a tonne, a similar story in that in the untreated control, there's no gain in profit, obviously. It's actually declining. But there is an increase in profit in the net return for deep ripping when you get out to 120 of N. But if you were to look at from the farmer's point of view at somewhere in that environment, somewhere between 40 and 80 of N, there is actually an economic case for deep ripping and applying N in that scenario, even at $1,000 a tonne. And just as a bit of supporting evidence, you may recall some similar slides I put up last year around a similar design that we had in Meckering. Different soil type though and different structure, but the outcome was actually the same in that in the untreated control, while we did see a yield response to N, it was basically just enough to cover the cost of N. Where we'd done the deep cultivation, even allowing for the cost of deep cultivation, there was profit derived from applying N. So if we look more generally at the soil types that we've covered in this project, most of our focus has actually been on water repellent grey sands. And in our trial work, we were detecting responses to K more frequently than other nutrients. So we've done a crop nutrient survey in collaboration with grower groups last year and this year. And the overall message there is that more often than not, potassium is the nutrient that is limiting yield post-amelioration. I guess that's happening for a couple of reasons. The first is that previously those soils are pretty unproductive and you wouldn't have invested a lot of money in them. But also those grey sands don't hang on to K. That leaches pretty rapidly, so they have pretty low soil K supply anyway. So the important point there is, in terms of low-hanging fruit, post-amelioration on grey sands, K is the most likely limiting factor. So I'll step through a couple more field experiments. The first is our site at Arano, where we were looking at interactive effects around deep ripping and K placement. And what we're really interested in here is residual effects. So this site has pretty high soil strength. The peak soil strength, as you can see from the figures, is at about 55 centimetres, so pretty deep and pretty hard as well, around 4 megapascals. Our deep ripping that we did in the first year persisted through to the second year. So that effect was certainly persistent, and you can see from the soil chemical analysis, pretty low K site, you'd expect a response to K there. And this is the summary of grain yield data over the 3 years. So wheat 2019, so we applied our tillage and K treatments in 2019. No fresh treatments were applied in 2020 or 21. So we're just trying to detect residual effects. So in the first year, while we actually saw treatment effects on shoot biomass and thesis, that didn't actually flow through to grain yield. It's pretty dry finish in that area in 2019, so that difference is closed right up. But in 2020, we did see residual effects. So I'll step through, unpack the treatments a bit. If we look at the middle figure, treatment 1 is our untreated control. Treatment 2 had K on the surface only, so 60 kilos of K. Treatment 3 was deep ripping to 50 centimetres, and then treatments 4 through to 7 were combinations of deep ripping with K either on the surface, deep banded, or with other nutrients, but combinations of ripping and K. So in the second year with Lupins, we didn't see a residual effect of K applied on the surface, didn't see an effect of deep ripping, but nearly a ton response to the combination of deep ripping and K, and no differences between the deep ripping and K treatments. When we go through to this year with wheat, a similar story, although we did actually detect a residual effect of that 60 kilos of K only applied in year 1. So that's treatment 2 compared to 1. No residual effect of deep ripping on its own, but again, about a ton response to the combination of deep ripping and K. So really importantly, on a really deep, very grey sand, we were able to detect meaningful residual effects out into the third year of deep ripping and K. Now that we have a few years of data, we can start looking at an economic perspective. And at this site, the deep ripping and K treatments had the highest gross margin over the 3 years. They were higher than deep ripping on its own, but not higher than the untreated control. So I guess a weak signal there around the profitability. That might change with another year of data from that site. But if we look at the figure on the right-hand side, it tells us an important story. You may not be able to see the black line on the far right. That's a line at 1.5%. We're looking at grain yield here plotted against shoot K concentration at anthesis. For sufficiency, we would expect it to be around 1.5%. All of the plots in that trial were K deficient. Even though we are detecting residual effects, there's still likely more yield to be gained by further K application. So a similar site, a similar design at a site in Minginoo, but the reason for going there was quite different. So this site is adjacent to one of our long-term K cycling sites. This actually has some of the lowest soil magnesium we've measured at any of our trial sites since I've been doing this type of work. It's also not a particularly constrained site, so it has had ripping and ploughing done in the past. So it gave us an opportunity to look to contrast different backgrounds of soil constraints. So at this site, it is a factorial of tillage treatments by nutrient management treatments, where the focus is on potassium and magnesium. So in the first year, we saw a response to deep ripping and rotary spading, but really not a lot in it. That's shoot biomass of lupins at maturity. As we get into the second year, those tillage effects actually weren't detectable in the second or third year, not a constrained site. But the nutrient effects came to the fore and saw some quite large effects. So I'll just unpack those nutrient treatments. The first treatment is our untreated control, so it gets no K or no magnesium over the life of the experiment. Then we have treatments that are 50, 100 and 150 of K, with or without magnesium, all applied in the first year, all at seeding. And our treatment on the right-hand side, the high control, is our positive control. That has 150 of K plus 20 of magnesium in the first year, plus 40 of K in the second year and 40 of K in the third year. So a notable feature there is that the high control, the yield is about 2.5 times the untreated control, so highly K responsive. But also importantly, we are detecting residual effects there of the 50 of K and 100 and 150 of K. When we get into the third year, a similar pattern, so wheat grown in 2020 and 2021. Again, the high control is about 2.5 times the yield of the nil control, and we are seeing residual effects of those K applications in the first year. But our first indication of magnesium playing a role in that 50 of K on its own is not enough to get a jump above the untreated control, but 50 of K with magnesium was. So it's actually our first indication that magnesium's possibly playing a role on that soil type. When we look at the net margin over the 3 years, remembering that the high control had the 150 of K plus 2 applications of 40, it was the highest net margin over the 3-year period. The same, not different to 100 kilos of K, so big applications of K. They were higher than the untreated control, and then we have these sort of weaker signals for the rates in between. If we look at the figure on the right-hand side, we see a similar story. We're looking at grain yield versus shoot K at enthesis, all certainly below levels that we would expect to be sufficient. Even though we've seen yield responses going into the third year, there's still yield to be gained by improving K nutrition over the growing season. So the work that we've done to date leading into this year led us to the view, I guess, that K management was likely to be the low-hanging fruit in terms of maximising yield potential post-soil amelioration. And so it's not about whether we need to apply K, it's how we do that the most efficiently and the most profitably. So we designed a series of experiments around treatments that included rate and splits. So I'll take you through the design of this before we get into the data. So we've repeated the same design at 2 sites here, at Dandaragan and Gamelling. The black is our nil control, the brown is 10 kilos of K drilled, 40 is the blue, green is 80 and yellow is 120. And the splits are shown in the table down the bottom. So they include either 10K drilled and some either at sowing or 8 weeks after sowing. So various splits. One of the questions going into this was how much MOP can we safely drill, because it's a pretty efficient way of getting K into the crop. How much can we safely drill without losing plant numbers to a point that reduces yield? And what we found is that there was actually no consistent reduction in plant density. Only at the Gamelling site, say treatment 6 versus treatment 1, where we drilled 40 kilos of K. But in other treatments where we've drilled 80 or 120 kilos of K, no reduction in plant density, and certainly nowhere near that red line, which is our threshold for yield reduction. We only have yield data for the Dandaragan site so far, and the responses were actually very small. So I haven't got the soil K profile here, but it was less than 15 in the subsoil, and I think in the 20s in the topsoil. So I expect it to be a highly responsive site. We only saw significant increases over the untreated control, where I've got the red numbers above the bars there. Those red numbers are our agronomic efficiency, so kilos of grain per kilo of K. The long-term average for the K to grain price ratio is 4.4. We need to exceed 4.4 just to break even and then to start making money. So that's not profitable, even at a site with extremely low soil K and soil constraints removed. And it seems that timing is a really important component of understanding why we're seeing what we're seeing. So here we have a comparison of the way we applied our potassium treatments and the way that we applied our basal N treatments. So in those environments, in our field experiments, we split our N 4 times to manage the leaching risk. And on the right-hand side, you can see that most of the shoot N concentrations are at or above critical levels for shoot N at anthesis. Whereas on the left-hand side for shoot K, where it's either gone out all at sowing or split with 8 weeks after sowing, we haven't been able to maintain sufficiency. So while we don't have treatments in there yet that includes the 4 splits, there's certainly an indicator there that timing is an important component. Just to give some perspective, I guess, on how different industries manage a similar soil type, though under different systems. The DPIRD's 3-phase program for vegetable production on those deep grey sands. In that system, they have 12 applications of K for a total of 340 kilos of K. And I'm not advocating that we go to those levels or even to that number of applications. It's giving an indication of what we need to do to improve our K use efficiency. So our inference, I guess, from those sites is that the K has leached. And some of the soil water monitoring that we've done at a different site for one of our soil amelioration by nitrogen sites at Badgingarra provides us a bit of insight. So we've got here an animation through time of the soil water profiles and the soil electrical conductivity profiles. The arrow is showing the current date, and you'll see the rainfall screen in from the right through to the left. You'll notice that for most of the growing season, soil water content will be higher in the black line in the surface. You might have to imagine it. So what that's monitoring has allowed us to do is to look at the EC profiles through time. So it's logged every 15 minutes. And at that site, we actually put out K at sowing and at 8 weeks, or 4 weeks after sowing, again to try and manage the leaching risk. You can actually see that EC profile move down with rainfall throughout the soil profile. The other aspect that's quite evident towards the end of the season is preferential flow. So part of the reason that inversion tillage has been adopted and is successful is that we're doing a better job of using the water that is there. And so even with the monitoring that we've done there, so it's only 3 pits down to 90 centimetres, you can actually see pulses of water at the end of the season in the untreated control move down through the profile, and they're bypassing the surface. So you can see preferential flow in action. So that is one of the underlying mechanisms behind poor water use on water repellent soils. I think we'll just move on to the next slide. So the next slide that I have, which you'll have to imagine also, is this one. So this is the 4th year from one of our long-term K cycling experiments. So this is at a site at Mingenew where there's been a long history of soil amelioration in terms of ripping, ploughing and liming. It was actually a really good opportunity for us to look at K cycling in an unconstrained soil. And what we were really interested in this series of experiments is how crop sequence influences K supply to the following crops. And so these trials, a series of trials, were set up to assess, from the point of view of this year, how does the preceding 3 years affect the response that I'm going to get this year? In general, our assumption is that it doesn't, but this demonstrates that it does. So when we do this, so what we're looking at here is grain yield of wheat on the figure on the left-hand side for 4 different crop sequences: a continuous wheat, a lupin wheat rotation, a wheat canola wheat rotation, and a brown manure wheat canola wheat rotation. So we're into the final W in all of those crop sequences this year, and the coloured bars are for different K management treatments. So the black is nil K every year. The K2 is just replacement K drilled every year, so what was taken away from that plot in the previous year is reapplied. The blue is 20 kilos of K top dressed at sowing every year. The green, 80 applied in year 1 only, and the yellow was intended to be our positive control. So 80 up front and then another 40 every year for 3 years. When we look at the stats, there wasn't actually an interaction here. So crop sequence hasn't changed the order of those treatments, but it has changed the magnitude. So if you compare, say, the loop weeper and rotation to the continuous wheat, there's clearly a step up in terms of grain yield. We're confident that those differences aren't related to N. So the way that we manage nitrogen in all of those trials is to measure actual nitrogen uptake in each plot, measure actual nitrogen removal, then we know how much organics are sitting there and we can calculate what's released in that year. So we've done the best we can to mitigate differences in nitrogen supply. We actually see a similar story here in terms of shoot N and shoot K concentrations. Up the top, on the right-hand side, we have shoot K concentration versus grain yield. So this is shoot K and anthesis. We've had 1 application for treatment 5, the K5. That all went on at sowing. All of those shoot K concentrations are below critical levels. For the N at this site, again, we've managed N leaching risk at this site with 4 applications, and we're all above, apart from a few points, above critical levels. So to summarise all of that, the deep ripping story is consistent in that deep ripping a compacted soil, and the compacted soil part of that sentence is really important. Deep ripping a compacted soil has changed the yield and economic response to N, and importantly from both of those sites, even at $90 a hectare, there is profit to be achieved with deep ripping and N in the first year. The tillage by nutrient interactions that we've seen depends on the level of soil constraint. So if you recall, our Arano site versus the Mingenew site, we saw an additive effect at a highly constrained site, really no effect of soil amelioration where there'd been a history of some amelioration being done. When we look at our whole suite of sites on those sands, potassium is the most likely nutrient limiting yield post-amelioration. And also, importantly, we are detecting residual effects. Even in those soils where leaching is obviously a risk, we are detecting residual effects. So it seems that there is an economic case for that capital application of K that hit up front before going into a more regular routine. Importantly, also, that there's possibly even greater yield gains than what we've observed in our field experiments by changing the way that we distribute K throughout the growing season. And finally, importantly, crop sequence and lupins in particular seem to have an important role on these sands in terms of improving K supply overall. So I'd just like to acknowledge everyone who's contributed to this work. It's quite a large body of work and a large group of people. My co-authors at DPIRD, Murdoch University, UWA, West Midlands Group, Levy and SEPWA, and all of that work is from 2 GRDC funded projects, which are at the bottom of the slide. Thank you.